Hello everyone. We are going to begin our first online lecture. So today I'm going to be going through the derivative rules for polynomials specifically. So that's that first box here. We'll be doing a couple of examples and I will give you a few practice problems. So it's possible we've already done this part of derivative rules. There are multiple sections of a calculus course. So if you've already done some of this, like if you were in the class, some of these classes before we left, and you already have some of this information, you can skip over it and go to the next part, or you might need the refresher and you may want to stay and listen to the examples again, but they are going to be the same as the stuff you already have. Anyway, do what you need to do to learn your derivative rules. If you want to skip to the next set, to the chain rule or to the quotient rule, because we already did the polynomials the week before we had left 2 weeks ago, then that's fine. Otherwise, we'll start through it. Alright, rule number 1. The derivative of a constant is equal to 0. Okay, that's what this says. This means the derivative of a c with respect to a variable x, c as a constant, is going to be 0. That's also the same rule down here, just in a different form. So if your function is just a constant, then the f prime x, which is what indicates a derivative, is equal to 0. So for example, derivative of the number 6 is 0. Second rule, and arguably one of the most important, the power rule. The power rule says if you want to take the derivative of x to the n, and that's also shown down here, if your function is x to the n, the derivative is nx n minus 1. So what that means is what I've done is I'm going to take the power, bring it down in front, and reduce it by 1. So, for example, if my function is x to the 5, according to the power rule, y prime, which is its derivative, is going to be 5. 5 comes down in front, x to the 4, because 4 is 5 minus 1, so I reduce the power by 1. Next rule. C f at x. So what this means is if you have a constant in front of some function of x, the derivative is going to be, well, that coefficient or constant sitting out front is not really going to have any impact right away. You're just going to take the derivative of the function of x and multiply it with the coefficient. So to give you an example of that one, so here's what it looks like. Here's the c, which is 3. Here's the function of x, x to the 4. So when I do the derivative, I end up with 3 times, and the derivative of x to the 4 is 4x3. So my result is 12x3. So what happens is that this number here comes down in front, multiplies with the coefficient, and reduces by 1 like the power rule suggests. So we end up with 12x to the 3. The second rule down here is indicating what happens if the function of x is just x. So it's one just that does happen often enough. It's actually the same as the power rule up here, but I never really use it as the power rule. I just know that when I have a coefficient in front of an x, and that x has a power of 1, that my answer for the derivative is just the coefficient. So this would look like y equal 9x. If I want the derivative of this, I know the derivative is just the coefficient, 9. Okay? And that's true anytime the function of x is just x. Okay? There's no x squared or x cubed or x half. If the function is just 9x or 4x, I would know the derivative is just 4. If it was negative 2x, I would know that the derivative is negative 2. So, and that makes sense when you think about it. If y is mx plus b, what would be your derivative? Well, my derivative of a constant is 0. The derivative of mx would be m. And if you remember, derivatives are just slope. So it makes sense that when we take the derivative of the line equation, we're getting m in return. So anytime you have just an x function, you're going to get the coefficient out front as the derivative. All right, the final rule in this box. What do you do when you have functions, or parts of functions, terms added or subtracted? So this has just the example for added, but it's the same for subtraction as well. Well, if I want to take the derivative something that looks like this. So it's something with a function of multiple terms. So I've got 3 terms here, 1, 2, 3 terms. I want to take the derivative. The main operations here are all the terms are separated by addition and subtraction. I don't see something that's going to look like the quotient rule or the product rule here. This is just multiple terms added or subtracted together. So to do the derivative, you would do the derivative of each individual piece in your derivative. So in this case, I would do the derivative of 3x squared. So the 2 comes down in front and multiplies with the 3 to make 6, and I end up with 6x. 2 minus 1 is 1. Derivative of minus 4x, so we just talked about this one above. Anytime you are taking the derivative of just an x term, the answer is the coefficient out front, including the sign. And the derivative of a constant we know is 0. So that's it for my derivative there. So that is your first set of rules for polynomials. We're going to do some practice with those now. But if you'd like to stop and post a question or ask a question, please do so. Otherwise, we'll keep going. Alright, we're going to find the derivative of the functions that are given. Let's start off with y equals 3. Y prime in this case I know is 0, because this is the derivative of a constant. S at t. So I've got a function here that's in terms of t. I'm looking for s prime. So my derivative in this case is built off 3 terms. I see polynomial, I see adding, subtracting, I see power rule. These all would work here. So first piece, derivative. 3 comes down in front, multiplies with the 1. 3t, 3 minus 1 is 2. Derivative of minus 2t, well, this is the same as, an x term. There's no power, so I know the derivative of a single exponent term is just the coefficient, so minus 2. And derivative of the constant is 0. So there's my derivative there. Alright, what's the derivative with respect to x of x to the 11? Well, that would be 11x to the power of 10, because I would bring the 11 down in front and reduce the power by 1. Okay? One of the things I want you to notice is notation here. So in the first two examples, I was given the functions, and I had to find the derivatives, and I denoted the derivatives by using the prime symbols. Okay? Whereas here, my function was within d dx. Okay? And the notation for d dx means the derivative of the function. So I was able just to kind of say that's equal to this. Please be careful when you're doing derivatives. Don't just keep writing, equal signs. You have to use proper notation to indicate when it's the function and when it's the derivative of the function, right? Because those are two very different things. We can't just keep saying the next line is equal to the next line and take the derivative and say that's equal to it. They're not equal. One is the function, one is the slope. So please do be careful of notation. Alright, let's do another one. Y prime in this case. So I have my function here made of multiple terms, 4 terms. I'm going to find the derivative of each term individually, since they're all added and subtracted, and that'll make up my derivative. So 3 comes down in front, 12x squared, minus 2 comes down, times 2, minus 4, x to the 1, 2 minus 1 is 1, plus 7x, so I know that the answer here is just the coefficient, because anything with a single term variable, like x or t or y, that's just going to be the coefficient, and derivative of a constant, and that is what pi is after all. Pi is just a constant, it just has a Greek letter to indicate it, but it is a constant, so derivative of pi is 0. Alright, next derivative. So this one's going to be similar to the one we just did. This is a polynomial that's been added or subtracted. So we've got 3 terms. We need to find the derivative of each one individually. So even with the fractions, there's no variables on the bottom, so we don't need to apply something like the quotient rule, for example. As long as there's no variables on the bottom and the top, in both places, there's no need to go into the quotient rule yet. We can still just apply the power rule, because this is just negative 1/4 x8 and plus 1/2 x to the 2. So there's no reason to do the quotient rule. We have just a variable on the numerator. It's still a polynomial. So if I apply the power rule to each term, I'm going to get negative 8x7 over 4 plus, the 2 will come down in front, multiply with the 1, and make 2x over 2, and the constant will be 0. Okay. So you do want to try to simplify these. In general, all I'm looking for in terms of simplification is reduce fractions, expand brackets if it's easy enough to do, to collect like terms, and don't leave any negative exponents. So you don't need to do a lot of simplifying or do anything too crazy. Just simplify, just clean it up a little bit so that it looks more proper. So for example here, we're going to reduce this down to 2, and we'll cancel the extra 2's there. So negative 2x7 plus x. The next one I'm going to show you is a little bit different. It's mainly to be an introduction to something that's going to pop up here and there, probably mostly next year for those that are going on to Math 20. But it's still a good thing to understand when it comes to derivatives. Sometimes there's more than one variable in your function, and you want to know how to deal with that. And the main way that we need to deal with it is we have to know what we're taking the derivative with respect to. So for example here, if I want to take the derivative of the function v, in this case this is the volume of the cylinder, and if I want to do it with respect to the height, so I'm saying I want to know how the volume is changing when the height is changing. Okay, and when it's changing, what is the change in the volume when the height is a certain value? So the goal here is to take the derivative with respect to h. So what that means is treat h as the variable. Alright, even though you have other letters like r, you're going to treat h as the variable. Okay, and for this next part to make sense, I want you to try to remember what our answer would be if you had things like 3x and you were asked to find the derivative, or negative 2x, or 7h, for example. If I was trying to find the derivative of 3x with respect to x, I would say my answer was 3, the coefficient, the part that's not the variable that's sitting out front of the variable. If I was doing negative 2x and I wanted the derivative with respect to x, I would say it was minus 2, because that's the coefficient that's not the variable out front. And 7h, if I wanted the derivative with respect to h, it would be 7, because that's the part of the front that's not the variable. So in keeping with that idea, my goal here is to take the derivative of this function, pi r squared h, and I'm going to treat h as the variable. Everything else will be treated as if it was a whole number, like 3 or 5. It's going to be a coefficient, or a constant. So when I say the derivative with respect to h, I treat h like my x. And right now I see h to the 1. So if I try to take the derivative of h, it's the same as doing the derivatives to these three. It would just be the coefficient. Well, in this case, the coefficient is pi r squared. Okay. And this makes sense when you think about the volume of a cylinder, which is what this is. And you ask yourself, what happens to the volume as the height changes? How is the volume changing? Well, if you imagine, how is the volume of that cylinder changing every time the height changes, even the smallest amount? And it really makes sense that you're getting pi r squared here, because that's the area of a circle. So as the height is slowly decreasing by the smallest amount you can think of, every little bit that height changes, you're losing an area of a circle. And that's how the volume would be changing as well. Okay. Alright. Something you're definitely going to want to keep in mind when you study related rates. Alright, let's do 2 more and then you can do some practice. Alright, so this looks pretty normal from what we've done before, with one exception. You might notice you have a square root. Well, that's okay, because you've learned a lot about roots this year's in Power. The main thing you want to do with a root is never leave it as a root. Change it to a fractional exponent. So root x is going to be 1/2, cube root will be 1/3. Change those roots as soon as you get them to fractional exponents. And the reason we do that is so that when we take the derivative And again, I have a polynomial that's been added or subtracted into 4 terms. I apply my power rule to each one individually. 3 comes down in front, multiplies with the 2, and reduces by 1. Here we have an x term, power of 1, so just an x, so I know that's the coefficient, which is just a 1. I may not see it, but I know there's a 1 there. Minus, here's our power, so the 2 comes down in front, power reduces by 1. Now, our term here, minus x to the half. Well, that's no different than what we've been doing so far. This is still just a power, it's just a fractional power. So it comes down in front, 1/2, and we're going to reduce the power by 1. So you're going to have x to the half minus 1. Right? And x to the half minus 1 is equal to negative 1/2. And again, if you're not feeling super comfortable with your fractions, you can always use your calculator. And there would be our result. So let's clean it up just a little bit. There's not a lot we have to do. There's nothing to collect in terms of like terms. There's not a lot we can do in terms of you know, expanding it or simplifying it too much. But the one thing we're going to do is get rid of that negative exponent. Now I'm going to leave it as 2x to the half. If you want to change that to a root x, you're more than welcome to. So if you want to change this last term here, it can read 1 over 2 root x if you want. Okay, that's also the same thing. Alright, so even if you're dealing with roots, it can still do the same thing. It's still just a power. Bring it down to the front and reduce your power, even if it's a fraction, by 1. Alright, one more. Y equals 1 over x. So y equals 1 over x, we want to find the derivative of this as well. There'd be 2 ways to do it. The harder way, or longer way, maybe not harder, but a longer way would be to try to apply the quotient rule here. Again, because you're seeing division, you might kind of instinctively try the quotient rule. And you wouldn't be wrong to do it, but it would be a longer way to do this one. Because this is a relatively simple quotient, you have a constant over a variable. The main reason you want to use the quotient rule is when you have variables over variables, x's over x's. But here we have a constant or a coefficient of 1 over x, or even 4 over x or 6 over x. You don't need the quotient rule for that. A nice easy way to apply what we've already learned here is to remember that you can move things up and down from fractions by putting the negative of their exponent. So this is actually the same as this. And if we know that, it makes doing the derivative a lot easier. So y prime would become, well, this is just a power after all. Even if it's a negative, the power rule still works. So if I do the same rule, x minus 1, if I bring the power down in front, and reduce the power by 1. Now be careful, sometimes people think it's 0. You want to reduce that power by 1, so you're getting minus 1 minus 1 minus 2. And you've got your derivative. So again, the only thing left to do would be to get rid of the negative exponent. So remember, you can only move things with negative exponents down, not negative numbers. So when I simplify this, I'm going to end up with negative 1 over x squared. So this is what moves down, but this stays where it is. Alright, let's try a few practice problems. So I'm going to write down 4 or 5 problems here, and I'd like you to pause the video and give them a try, and then I will go on with the explanations. Okay, so I'm going to write them out, pause for a second, but I'm just going to keep going on with the solutions, but I'd like you to pause and try them before you listen to the solutions and see the solutions. Alright, so here are the 5 questions I would like you to try. So remember to use proper notations when you're writing the solutions to indicate the derivative. And give them a try and go from there. Alright, solutions to the practice problems. So hopefully you paused and gave them a try yourself before looking at the solutions. So I'm going to go through the answers. So number 1, y prime. So if I'm taking the derivative of x plus 1, the derivative of x is just the coefficient, so 1, and the derivative of 1 is, well, it's a constant, so it's 0. 2. So when I take the derivative of 3x6 plus 5x, I notice I have addition subtraction of 2 terms, two terms of a polynomial. So I'm going to apply the derivative to each term individually. I take note that I have a power, so I apply the power rule. 6 comes down in front, multiplies with 3, and I get 18x5. Plus the derivative of 5x. There's no power on this except 1. But I know that anything with a power of 1, as you know, my variable with a power of 1, the derivative is just the coefficient, sign included, so plus 5. Derivative of negative 15x, again, there's no power per se, there is a 1, but when it's a power of 1, I know the answer is just the coefficient, so negative 15x. Negative 15 is the derivative of negative 15x. Alright, the last 2. So, I've got derivative of 2 terms being separated by a subtraction. I'll do the derivative of each term. Just make note that there is a square root x, so I'm going to turn that to x a half. Actually, how about we just write it down here? So y equals x5 over 15 minus 2 root x. That's the same as x5 over 15 to x half. So when I do y prime, I apply derivative to each term. 5 will come down in front, and I'll subtract the exponent by 1. Minus, now I've got the derivative of the second term. So, same thing, I will bring the exponent down in front, and I'll have 2 times a half. X 1/2 minus 1 is negative a half. And all that's left is to clean it up a little bit. So, this one I know I can reduce, x4 over 3, and this one I can cancel this. And I can bring this x negative a half to the denominator. So I have minus 1 x half. Okay? Or again, if you want to write that as root x, that's fine. Okay? You don't need to go so far as to put these with a common denominator. That's not necessary. If you want to try, go for it. You're more than welcome to. Something like that would look like this. So we have a common denominator of 3x half. This would have to be multiplied by 3 both ways. What happens here is that this gets multiplied by x to the half, which means you have to add the exponents, so 4 plus a half, giving you 9 over 2. So it doesn't really add a whole bunch to put it as a common denominator. That's certainly not necessary. Just if you're curious, you want to see what I meant by a common denominator, that's absolutely optional. I wouldn't do it unless you feel confident in doing it correctly, because if you do it wrong, I have to mark it wrong. So this is enough. All I really need is to see any like terms collected, move negative exponents down or up, just get rid of the negative exponents, reduce any fractions. Again, just clean it up a little bit is enough. That's a simplified answer. Okay, at least for me. Alright, the last one. So you're going to do d dx of number 5. There was 5x to the 4. Then it said plus 2 over x. Now I'm going to change that because I know that 2 over x is the same as 2x negative 1. And it had minus the cube root of x, which I know is 1/3. Right, the goal is to turn whatever you can into a power, because the power rule is our usually our simplest way of doing the derivative. So if we can make a power rule and just simply apply a single power rule to get the answer, that's the best option that we'd want to try and use. So I turned everything in that question number 5 into a power, the 2 over x and the cube root of x. And now I'm going to apply the power rule to each individual piece to get my answer. So the 4 will come down in front to make 20x cubed because 4 minus 1. I'm going to have minus 2, negative 2. So negative 1 comes down in front and multiplies. Minus 1 makes minus 2. And minus 1/3 x and 1/3 minus 1 makes negative 2/3. Okay, again, if you feel at all uncomfortable with your fractions, remember, you can absolutely use a calculator. So 1/3 minus 1 is negative 2/3. Okay. So again, there's no reason to worry too much about your fractions. I would love it if you could do them by hand, but if you can't, when in doubt, use a calculator. Okay. All calculators have the ability to make fractions. All scientific calculators, anyway. Alright, so the other thing I'd like to do here is just clean it up. So let's get rid of the negative exponents. I don't see anything else that I can do. So that's good. And that's good there. So that's enough. We don't need to start playing with common denominators like I did up here. That's not necessary. Again, if you want to, just for the heck of it, just to see, go ahead. But that's enough. We're just trying to simplify it a little bit. Okay. Alright, so that is the first set of derivative rules. Those are your polynomial rules. They are probably some of the most important rules because they will be used over and over again when you do other rules. So definitely make sure you've got a good handle on those. Do some more practice into your book. Try some videos if you need to. I think there might be some extra practice even if you look further down in the additional information. Otherwise, ask some questions if you need to. Once you're ready, move on to the next video.